Okay, again, thank you so much for joining today's seminar, Introduction to Probability. This is like an online seminar number 82. Okay, let me introduce myself. My name is Kan Nishida, CEO at Exploratory. We built Exploratory 2016. So since then, we have been working to democratize data science by building Exploratory as a tool to do the data science tasks, and also providing the training and the seminars to share our knowledge and experience. And our vision is data-informed decisions making is essential to make the world better. Therefore, we can contribute by democratizing data science, and that's our mission. And when we say the data science, we mean like accessing the data, transforming, cleaning up the data, we call data wrangling, and visualizing and analyzing the data with various machine learning and statistical algorithms. And then once you get the insights that help you answer the question, the business questions, then you want to communicate with other members, other stakeholders in your organization, or maybe outside the organization. So communication is also the important part. And Exploratory provides a modern and simple UI experience to do these 5 pillars of the data science works. Okay, so having said that, the Exploratory Online Seminar number 82, this is the Introduction to Probability. The goal here is not so much, I'm not an expert on the probability or probabilistic theory, as you can already find out the way I pronounce, but this is actually essential, sort of like a foundation to build build sort of like statistical theory. And then eventually, like I like to move on to like a hypothesis testing, and then maybe regression analysis, and then multivariate analysis, and so on in coming weeks. But in order to get there, it's very important to understand the probability itself. So this is sort of like motivation for me to do this introductory course of the probability. Okay, so it's going to be not the deep area of the probability. It's more like a basic, sort of like a essential part of the probability. This is the things that you want to understand so that you can go to move to that later on, other topics like hypothesis testing, confidence interval, and statistical inference, and so on. Okay. So today's agenda is what is probability? This is a basic. So some of you might have already known, but I just kind of set the sort of same foundation. And then I want to also touch base on a probability and statistics. And like I said, my motivation doing this seminar is to eventually move on to the statistical inference or hypothesis testing and so on. So therefore, it's very important for us to understand the difference between the probability and the statistics. And also in coming seminars as well, when I say probability, most of the time, I mean it as a frequentist interpretation of probability. You might have heard about this word. If you don't worry about it. I'm going to actually touch base later on. But how you understand the probability is actually more ambiguous in the real world. People actually use their own way of understanding it, but I just want to kind of make it clear, and the way we use, or that way people sort of like supposed to use in the world of statistics. Okay, and then the last topic is the one is sort of like a little bit of segue for the next seminar. So that's how the probability can be used in statistical inference, or even like I just expand the area to be like more statistical thinking. So I think that's a very, to me, it's the most important, interesting part. Okay, so let's go one by one. What is probability? So probability theory is a doctrine of chance. It tells you how often different kinds of events will happen. And the last part is actually, sometimes people get surprised on this, which is, it is a branch of mathematics, so the mathematics discipline, and then not the branch of statistics. Maybe you guys are not, but I somehow got totally confused because for my life, first time like I studied statistics and then quickly gave up when I was at college was I think it's almost like at the very beginning we learned the probability as part of statistics class. So that's why like I thought somehow the probability was a part of the statistic. I got totally confused, and later on I realized those are two different things. But I'm going to go over the difference more in the detail later. So anyway, so I'm going to have one question here. So what is the chance of me eating one of these at lunch today? I know it, but people, you guys don't know it, right? So there's a left-hand side top and ramen, which is most my favorite. And then the next one, the udon, which is a noodle, but it's like a thick wheat-based noodle. And then the curry, I don't know you guys know it, but Japan, there was a curry rice, which originally I'm sure came from India, but Japanese developed their own way of making a curry, which is very different from the curry in India. But anyway, so there's the curry rice. And then the left-hand side bottom is a spaghetti, which is bolognese spaghetti. And then the middle bottom is a burger. So 5 options I have. And in probability language, we call these things as elemental event. So each of them is a sort of like a basic like element, right, of a given event. So either I eat ramen or I udon or something like that. So now there's several rules in the probability. So one of them is every time we make an observation, then the outcome will be one and only one of these events. Otherwise, we can't really talk about the probability. So what that means, so when it comes to lunch, I have to select one of these. I cannot just say like, hey, I'm not going to select anything, or I'm going to select something else. Like if we are talking about the probability of these 5 elemental events, and which out of which what is going to happen with what percentage or what probability, then I have to select one of them. Okay, that's kind of like obvious. So then instead of like kind of guessing around, like I wanted to know like myself, like which one like I tend to pick for the lunch. So I have recorded that what I eat for lunch every day. And then I did that experiment maybe like 1 month or 2 months or whatever. And at the end of the days, I draw the chart. Right. Okay. So if I ate, for example, like 10 days for ramen, 20 days for udon, then like I can create like some kind of a bar chart, right? So I just wanted to see like what is the frequency of each food. Then once I get those numbers, then maybe I can calculate quote unquote probability of me eating which dish. So here's a chart that I came up with. So ramen turned out to be the highest. Most likely, like I eat ramen, basically 40%, and pasta 25%, udon 10%, and so on. Okay, so that part. So this is a percent. So like let's say like I ate like 100 lunches. Then out of that, like 40 lunches what happen to be ramen. So that's what this means. Okay, so the probability, like often we use P and bracket, and then that basically indicates the probability in a sort of like a fictional, like like a textbook, way of expressing the probability. So P bracket event of interest, P stands for probability. And then how you calculate is that like a number of events of interest, in this case, for let's say like ramen or something, the number of events of ramen, how many times happen, and then divided by all possible events, like out of like, let's say like 100 lunches, they're divided by 100. So in this case, the chance of or probability of me taking the ramen as lunch is actually 0.4 or 40%. Okay, so that's that's how you just use that P notation. Okay, and then that once you have this or probability ranges from 0 to 1. So 0 to 0.5 and 1, or obviously 0% to 100%. 1 means 100%. 0.5 means 50%. Okay, so if the ramen, the probability of ramen equals 0, that means 0% chance that I would eat ramen, right? So that means even today's lunch, we can expect 0% chance that I would eat ramen. But if it's 1, that means all the time. If I had 100 lunches, I eat ramen all the time, every day. Okay, so that's 100% or 1. And if it's 0.5, that means I eat ramen every other day or once in 2 days. If I had 100 days, I ended up eating 50 days of 100 ramen. Okay. Then another thing, this is also another rule in a probability, is that it's kind of obvious, but all the numbers can be added up. And that number has to be, the sum of all these numbers must be 1 or 100%. It cannot be 120% or 95% or something like that. Once in a while, when you do the rounding of the numbers, then you ended up like the number tend to be like 101 or 99 point, whatever the numbers. But unless you round the numbers, that kind of stuff, like it has to be 1 or 100%. Again, this is obvious, but just to make sure we are on the same page. And there's something called group event. So let's say probability of I would be eating noodle at the lunch. And what is that probability? What's the chance of that? So in this case, ramen, pasta, and udon, those things are actually noodle. And a burger and a curry, those are not noodle. So what is the percentage of I'm eating these 3? And that's actually pretty simple. All you need to do is just adding them up. So P bracket ramen plus P bracket pasta plus P bracket udon, which is 40% plus 25% plus 10%, which is 75%. Okay. So that's how and there are a bunch of more way of like doing this kind of calculation. Like what if like A plus B, or ramen no pasta, or ramen pasta or udon. There are many way of like calculating the probability, but this is the kind of basic thing that at this point so far we need to know. Okay. So let's move on to the next topic, which is probability and statistics. So these two things are deeply connected, but they're two different things. So probability questions are something like this. So for example, what are the chances of a fair coin coming up heads 10 times in a row? Okay. Or how likely is it that 5 cards drawn from a perfectly shuffled deck will all be hearts? Or what are the chances that I'm going to win the lottery, whatever the lottery could be? Okay. So important thing is that when you talk about the probability, we know the truth. Okay. So that means, so the coin is fair. There's no gimmick or anything like that, just a regular coin. So therefore, there's a 50% chance that any individual, anybody, coin flip will come out with heads. So we can assume that's correct. Second one is I know that the deck is shuffled properly. We're not talking about magician here. We're talking about just regular random person. And then we made sure the deck was shuffled properly. The third one, I know that the lottery follows specific rules. I have no idea what the rule actually is, but it's not like they're cheating so that like they actually pick and choose who to give it to. It's more like they have a set of rules, sort of like kind of random based rule, so that everybody has sort of the same share of winning, right? That's chance of winning. Okay, so we know the truth. And in probability theory, we have a model that is obviously correct and everybody can agree with. Therefore, we can build additional calculations on top of it, or build logics on top of this model. In this case, the model means that P bracket, in this case, heads equal 0.5 or 50%. Okay, so the calculating this number is obviously like the possible options is heads and tails. And then like we're talking about like we're interested in getting heads, so which is one. So like when you flip the coin the next time, so only like one of two, and happen to be in this case heads. So therefore, like what's the chance of that? Okay, so that was a theory. Okay, but now let's flip the coin 10 times in row and see what will happen, right? So notice this, like before, like I was talking about sort of theory, the probability is a theory, more like deduction kind of thing, right? So if you're familiar with that, that terminology. But here, like what I'm trying to do is I want to see that is actually true in the world I exist, I live in the real world. What will happen? I want to observe. And then so I throw the coin, and then first I got the tails. And that's sort of like, yeah, the 50% chance I would get tail because 50% chance I would get heads. It's basically the same thing. So I got tails. Okay, that's fine. The second time I throw, and then I got tails. Okay, well, with the 50%, so who knows? I mean, like, you get, heads or tail. And the third time I got tails. Okay, sometimes something like that can happen. And the fourth time I got tails. Oh, that's interesting. I keep getting tails. That's weird, but I'm sure just the luck. And then I finished this flipping the 10 times, and then I ended up getting 3 heads and 7 tails. Okay, so that's interesting because that model told me that I should get heads 50% of the time. But this is not 50% of the time. This is actually 30% of the time, 3 out of 10. So let's try it again. Maybe that was some kind of fluke, and I did that again. And then, ideally, like I want everybody to flip the coins at this time while you're watching. But obviously, we don't have time to wait for everybody to finish. So I'm gonna just kind of use this fictional thing. But either way, like you're gonna get a similar result, right? So this time I got 7 heads. This time so I got more heads, but 7. So that means 70%. So that's okay. That's interesting. But nobody actually would be surprised. I mean, if you have done something like this, even like a dice or a coin or anything, usually like it's kind of the result would never be like just exactly 5 out of 10, right? So like I keep doing this on like a third time, fourth time, fifth time, and sometimes I got all heads. Sometimes I got more tails. Again, somehow it's almost like kind of like a random. So the point here is we don't know what will happen in real world, even though we know the theory, but the real world can be different. So the probability is we know the model. In this case, the model means just very simple. It's not like machine learning model or anything like that. It's just a model or the formula or whatever that explains things. So the P bracket heads equals 0.5. That's the model. But we don't know that data. We don't know what's going to happen in the real world. Okay. So now, as opposed to the probability, so statistics or statistical inference in particular is what what that is. So my friend flipped the coin 10 times and it came up heads every time. It's all head. I'm sorry, this is Japanese, but it means heads. And was there any trick or was the coin flip fair? Those are the questions that actually the statistical inference can help you answer rather than the probability theory. Okay, so if the coin flip was fair, then the appropriate model would be the one which says that the probability of getting heads is 0.5 or 50%. However, if the coin flip was not fair, somebody did something, then the appropriate model would be the one which says that the probability of getting heads is not 0.5 or 50%. Okay, I'm sure there are a bunch of other models as well. It can be like, it could be 0.3, it could be 0.8. But here I'm trying to simplify here is that either 0.5 or not 0.5. So we have, possibly like two models here, right? Then the statistical inference is different from probability because in statistics, we don't know the truth. Truth meaning like, what is the truth about this, coin flip? Like we don't know like if somebody did some trick, behind, or this person who is flipping the coin had a very weirdly special skill, or we don't know. But we have data. Actually, this person like flip coin 10 times and then we got the result. That's the data we have. And the statistical inference is about inferring the truth about the world, in this case, flipping the coin or the coin itself, by figuring out which model fits better with the data that we have. In this case, we can say like we have data and which model would be more appropriate. And that's the kind of thing that we statistical inference can do. So therefore, you see this, the difference. The probability itself is more like a theory, and the statistical inference is actually use the data and also the theory, but make sure, or the figuring out the theory and the data or reality matching or making sort of a consistent or not. So that's the statistical inference. Okay. So now like next one is the interpretation of probability. So we kind of like went through the whole probability things and then we pretend like we understand, what 80%, 60% is a probability and then that's, what that means. But we are actually not really understanding. So I'm sure like you guys might be understanding, but it's actually not really clear for many, including me some time back. So how should we take the probability in real world? So we use these words, right? So like a possible, chance, likely, probable, every day on the news or a conversation or whatever. But what does these words mean? Right. So for example, let's say like United States and Japan will have robot baseball games. It's a robot, it's not a real human. But then we are going to bet which team will win. And let's say we decided that the probability of United States win as 80%. Okay, so that 80%, what does this mean? What 80% mean? So a couple ways to interpret these numbers. Number one, if we let these are robots, right? So like they can play the game again and again, sort of kind of simulations. They never get tired. So we let them play again, again, again. And then at the end, United States would win 8 out of every 10 games on average. So that's actually 80%. Another way to understand this probability 80% could be if you bet $1 on Japan and Japan won, then you'd win $5. You will get your $5 back, the initial money you bet on. And then plus you get the $4 reward. And also then at the same time, if you bet $4 on the United States and the United States won, you'd win $5. You will get your initial $4 back plus the $1 reward. So there's a difference, right? Like if you bet on Japan, like you get more money. If you bet on the United States, you get it's just a little money. That's because we already know that 80% of the chance the US will win. And we are betting on that. That's why there's that difference. Okay, so this is the interpretation 2. Number 3 is my subjective belief in the United States winning is 4 times stronger than my belief in Japan winning. I think this is more the way of like understanding probability. Most of us, like when we talk about 60%, 80%, usually this is what we really sort of like thinking but inside our head. Okay, so this is a subjective belief. There's no sort of like a quantitative thing or anything like that. It's just that like, hey, I think it's more chance of the United States winning, right? It's like, it's the 80%. Come on, like we know that, right? So it's a sort of like our human intuition kind of based approach. Okay, so these 3 interpretations are 3 different ways of understanding that number, 80% of probability. So that's why like I listed them up. Okay, and then to understand or like, what are, so how we should go about it is that there are two ways of understanding. There are other ways too. So main thing is a frequentist and a Bayesian. And I'm sure like you guys might have heard of it, but a frequentist is, these are the two big disciplines in the statistics, by the way. So frequentist way of understanding is a think of probability as a long run frequency. Okay, so when we observe events repeating over and over again, almost like infinity, like over and over again, and it is a proportion of a given event happening. So let's think about a coin flipping case, right? So like we know like a P bracket heads equal 0.5 or 50%. So what does this 50% mean? So you flip the coin first time, you got the head. So it's at this point, 100%, not 50%, it's 100%. And then you flip the coin the second time. So that again, like you get heads. So now at this point, you get heads, two heads out of two flips. So therefore it's 100%. The third time, again, you got heads and 100%. Fourth time, now you got tails. So therefore, three heads out of four flips, meaning 75%. And the fifth time, sixth time, seven times, you keep repeating this. And not just 7 times, how about like repeating 100 times or 1,000 times? So what is going to happen is that here's a chart. Y-axis shows the proportion or the probability of the ratio of getting heads. Okay, so 0 to 1, 1 means 100%. And then the x-axis means how many times you flip the coins. So when it says 100, that means 100 times. Out of 100 times, how many heads came happen at this time of being observed at this point? When you see 600, that means you throw coins 600 times. Good job. But you threw 600 times. Then at this point, how many times you got heads? And then based on that, you calculate the proportion or the ratio or probability. Okay, so what happened is like at the beginning, it started with 100% or 1, and it went down and up, and it sort of like it varies largely. But then like the more you throw and the more you throw, and eventually like it's kind of coming down to the number, in this case 0.5, which is a theoretical probability numbers. Because probability number in this case was 50% if there's no weird stuff was happen in the coin. It's a fair coin flip, and it's supposed to be 50%. So it becomes kind of like a settle down to sort of like the numbers that it's supposed to be. And if you repeat this experiment itself, like you stop this experiment 1,000 times of coin flip, and then you're gonna restart. You're gonna start from scratch, and then do that couple times, and then but every single time you're gonna get similar result. Maybe sometimes the numbers start from 100%, or maybe sometimes start from 0%, because if at the first time you flip the coin, you get the tails, then that means it's 0%. But always at the beginning, it's going up and down, but eventually settle down to the number that is supposed to be, which is the model that P bracket heads equals 0.5 is supposed to return, right? Okay, so that means with probability theory, we can't predict what will happen next, but we can predict the probability of the aggregate behaviors over a sequence of events with high confidence. And this is called law of large number. So in this case, we had like, we don't know, like maybe like a 10 or 20 times is like a small repeats. Like it could be 75%, happen to be. But if you have like a 200 to 200, 300, if you have more times, then we can predict, oh, it's going to be like a 50%, right? So, so that's called law of large number. And this concept is very important when you understand the probability in the statistics context. Okay, so now that's, by the way, the way of frequentist understanding of probability. And the frequentist view of probability is considered as objective. because probability statements needs to refer to a sequence of events that occur in the real world. Real world means in that case, even though that coin flip was kind of like a simulated one, like I didn't throw the coins like 1,000 times, but even if you do in the real world, and you can actually get a very similar result. So, and also like any two people watching the same sequence of events unfold and trying to calculate the probability of an event or proportion of that event must come up with the same answer. In this case, 50% and 50%. So two people came up with like, one is 30%, another one is 70%. No, that's not going to work in this frequentist view. It's always like one same number. What happened? The two people came up with different numbers. Well, one must be wrong in this case. Of course, two of them can be wrong, but at least one must be wrong. So two of them cannot be right at the same time with different numbers. That's a frequentist view. And the other one is the easy way to contrast between these two is Bayesian is more subjective. What subjective means is you can assign the probabilities to any event you want to, even including the events that are not repeatable. So the coin flips is like in case we repeat it hundreds of times, but you don't have to repeat. Like, hey, like I just did one, and there's certain things you cannot repeat in this world, but no problem. You can assign the probabilities. Define the probability of an event as the degree of belief. This is a key part, degree of belief, that an intelligent and rational agent, or rational in this case, people, assigns to the truth of that event. So the degree of belief, what that degree of belief mean? Well, it's actually, that's the subjective part. That person, it depends that particular person. So probabilities don't exist in the world, but rather in the thoughts and assumptions of people and other intelligent beings. So it's more like a theory, right? It's more like in your head. That's why like your confidence is, let's say like, hey, I think the US is stronger, like probably like 4 times than Japan. Like it's just that's actually in your brain. It's not like the numbers on the paper based on the data or anything like that. So that's what the subjective means. So the frequentist, again, it doesn't allow any two observers to attribute to different probabilities to the same event. When that happens, then at least one of them must be wrong. As opposed to the Bayesian world, it does allow everyone to have their own beliefs. I can believe a chance of getting heads with the coin flip is 70%, and you can believe it to be 30%, and that's okay. We are both rational, but it's okay because it depends on like my degree of belief as opposed to your degree of belief. So going back to those 3 ways of understanding probability, the first one, if we let those robots play the game over and over again, United States would win 8 out of every 10 games on average. That's a frequentist way of understanding. The second one is actually not the frequentist nor Bayesian. It's actually something called odds. So it's more like odds. I'm sure like you had heard about when you do the gamble. I'm not sure you do the gamble, but you often hear this word. So that this particular idea is odds. Odds is another topic, but I'm not going to go into detail. But sort of like what's more likely to get one outcome than the other. So that's really the odds. Then the third one is the Bayesian. Okay, I just wanted to clarify these differences because when I talk about probability and if I step on some kind of some lines and people actually complain, so like I just wanted to clarify. And then in this seminar and also coming future seminars, we are going to use frequent disinterpretation of probability. So having that said that, let's go in. But however, there's one problem. So that is that what if such a sequence of events doesn't happen in real world? So that's a problem because frequentist view requires that events happen like over and over and repeat over and over again. But let's say when you look at the weather forecast and it says, hey, there's a 40% chance of rain tomorrow. And then tomorrow meaning like, February 22nd, 2023, or whatever the particular day in Sarasota, Florida, which where I live. Okay, so what this 40% means is that, does that mean that you try to understand this like more frequent this way? Okay, maybe, if we have 100 people go outside and out of 100, 40 people get wet. Is that what it is? Or the second maybe way of is that maybe like if I go out and then let's say like I count it like every minute or something, and then like, I had a 100 minute and then out of 40 40 minutes I got wet. That's what the 40% mean. Or maybe like when I see on the ground and then like I had a square feet or something, and out of that like only 40% of the area get wet. Because if that's the case, then I can actually calculate these numbers as a sort of like might not be repeating, but sort of like more objective way based on the numbers. However, none of that is actually true here. So what does that mean in the frequentist terms? Okay, because the problem here is that there is only one Sarasota, Florida. So it's not like, hey, we have the 100 cities and then like out of 100, we have like 40. Or there's no such things. And then tomorrow comes repeats over and over again. Like every day that you wake up and there's a tomorrow, right? But in this case, the February 22nd, 2023, one particular day, and it never comes back again. Like I wish it comes, but never. So it's only once. And then tomorrow, when it comes, we expect either rain or no rain. There's only one of those two. So this makes it hard for the frequentists to interpret probability, is it? So this event of raining tomorrow won't repeat over and over again. So we can't say like, it's not like a coin flip. It's like, hey, like if we repeat this 100 times, like out of like 40, right? We can't say something like that. We can't assign probability to a single non-repeatable event. This is not Bayesian. You remember, this is a frequentist way. So like we cannot assign the probability if that is not repeating. So what are we going to do? Well, it's actually the way to understand this is not the we are just kind of like you need to twist that things. So there is a category of days for which it predicts a 60% chance of rain. Sorry, this has to be should be 40%, but let's switch that to 60% because the slide says 60% now. But anyway, so that predicts a 60% chance of rain. Let's assume that like we such days, okay? Because every day, let's say 365 days. I'm sure this forecast station says 60%, many days through the year. Right, so it's not just only one day, many days. I don't know, 30 days, 40 days, who knows? If we look only those days that forecast predicted 60%, let's imagine that there were like 30 days it predicted, out of the whole year. Then the 60% of those days it will actually rain. So that's what the frequentist way of understanding. So when you have the chart, x-axis is the chance of rain or probability of rain. Okay, so this is basically when the forecast says 50%, 60%, that's actually on the x-axis. Y-axis is a little bit kind of twisted. So how many, out of 365 days or out of 5 years, whatever that could be, what are the percentage of the days that actually rain? Okay, so that's that 10%, 20% y-axis. So ideally, if we draw the line, all the dots, every single time the forecast says 60%, 50%, then it should be on that sort of like a diagonal from the starting from 0, 0 on the left-hand side bottom to all the way to the right-hand side top. So that's the chart. So when you look at the dotted line, so that's that theoretical probability means. Okay, so the chance of rain, when it says 60, that means it should be on the 60 on the y-axis because 60% of the days it says 60% raining, ended up raining. So that's the dotted line. And then blue solid line is the one actually coming from that one of the weather forecasting station. It's not actually, this is actually, I think it was like not the TV. I thought like NCAA or some kind of more national level at a government level organization forecast. And then when you compare, it's actually pretty matching. But theoretically means it's in theory that dotted line is the one that is at a 40% means or 60% means. Okay. So now you know it's a kind of little bit weird way of understanding the frequentist way of understanding probability. At the end, to be honest, I don't really think about this kind of thing every time like I get the probability. I tend to think Bayesian way, but when you use a statistical tool, especially based on the frequentist ones, which is most of the stuff you see and you use, and then in exploratory, most of the stuff is actually based on most of statistical algorithms based on frequentist probability. So so that's what this means. Okay, when you see the probability in the precise and accurate explanation, basically based on this understanding. Okay. So then last not least is the probability, how the probability is used in statistical thinking. To do, I want to use one example. You know, like when you go to whatever the event, in a party or something, like there's always one guy or one girl telling me, I can tell the difference between French and California wine. I mean, like, you know, I'm sure I just lied. There's no, it's not always, but you know, sometimes once in a while, you see some people pretend like they know the wine. It maybe not be the French and California wine, but they pretend like they know wine. Okay. And then like I think about myself, it's like, is it really, is this guy really true? Or maybe he's just saying it, or maybe he knows what he's talking about, right? Okay. And usually like you start having a conversation and you figure it out, like if you know the wine, but otherwise you don't know if that's true or not. So what we do is we do the blind tasting, right? So this is how we test the people to be, you know, people have enough knowledge about wine to be sommelier or no. But anyway, so we pick wine glasses filled with either California or French wine in random order, in a random selection, and serve them without labeling and ask this person to say, which one is this, California or French? Okay. And then remember, this is basically like you have only two options, California or French. It has to be one of them, right? So it's the same thing as a coin flipping. So the probability of coming up with like a California, if you don't know anything, if you randomly selected, it should be 50%, right? So even like I love both wines, but I don't know like which one. So to be honest, so you know, I just randomly said like, hey, maybe French, maybe California. But even then, like I can just, you know, sort of like come up with 50% of a chance to be correct because just a coin flip, right? Okay. So the first one, the 50%, and the second one, again, it's like a coin flip. Maybe like, you know, out of, you know, either California or French. So 50% of the chance I will be right. The third one is the same, and every single wine glass should be the same. It's not like, you know, you have, we know like which glass, I mean, sorry, like how many of the glass has to be French or California, that kind of stuff. And they don't tell me the answer every single time, right? So like no information like that. So it's 50% for each glass. Then the probability, again, is that we know the model, okay, but we don't know the data. So if assume that we don't know anything about the wine, okay, this person is doesn't know anything about the wine, but still you can answer randomly and being correct 9 out of 10 glasses, even without knowing anything about the wine. That can happen, right? So if you don't know anything about the wine, supposedly like 50%. So that means you have the 10 glasses, you should be able to answer like a 5 being correct and 5 being wrong. That's a 50%. But you might be correct 9 out of 10. Doesn't mean like you know it, but you just randomly answer it. And opposite case can happen too, like 9 times is wrong and then 1 time is correct, right? But you remember the law of large number, if you repeat this again and again and again, eventually settle down to theoretical probability. In this one case, of course, we are not going to repeat because you want to get super drunk and die. But just think about sort of like a thought experiment. So first time you answer randomly and about being correct 8 times out of 10. Okay, so this happened just randomly. You don't know anything about the wine. And then so right hand side, I put the bar on the 8 because x-axis in this case of being correct. How many times you're correct? Okay, and then I'm going to kind of accumulate this block on the to the it's sort of like kind of block piling. The second time I got 5 times out of 10 was correct. And the third time, and it's how many? 3 times out of 10 were correct. And then the fourth time, sorry for the Japanese at the top, but it was just a number, number 4 times or something. But fourth time, so 3 out of 4, 10 are correct. So now, like at this point, right-hand side chart, I have a 2 for the 3, and a 1 for the 5, 1 for 8. And the fifth times, I got 4 times out of 10 correct. Okay, so you repeat this 10th time, 20th times, and then 30s, 40s, and then 50s, and then 100. You keep repeating and repeating again. And then right-hand side is the chart started looking like sort of like normal distribution kind of shape. So the center is the highest, and then when you start going to the left and right, start going down. Okay, so this is kind of like a simulation. It's not like we did 1,000 times of drinking wine, but nonetheless, if we repeat this experiment over and over, it will end up with an asymmetric distribution of having 5 at its center. 5 means 5 correct answers out of 10, or 50% times correct. Okay, so this is, if we assume it's like just a random, but based on 50% chance probability. And this type of distribution looks like a normal distribution, but this one is called particularly binomial distribution. It's very similar to normal distribution. The difference is x-axis is not numerical. It is numbers, 0, 1, 2, 3, 4, 5, but there is nothing between 4 and 5. There's no such thing as 4.5 or 4.2 or something like that. Sort of think of it as kind of category, right? Like 2, 3, 4, those are two different things. However, those are numbers. So that part is a little bit confusing. But anyway, so this is called binomial distribution. I'm not going to go into the probability distribution in this seminar, but it becomes kind of this kind of shape. And you remember the probability, there's one rule, one of the rules is that all those ratio numbers, when you add it up, there has to be 100%. So that means this chart, when you have this distribution chart, then you can calculate the percentage or the probability of particular number, let's say like 8 or 9, based on the ratio or the proportion. So for example, being correct 10 times being correct, right? So if I did this and randomly, and then somehow like I got a correct answer 10 times, I was so surprised. But that is, we are talking about 0.01% of the chance. It's not going to happen so often, but sometimes happen, but rarely happen. How about 9 or more times, 9 or 10 times and being correct? That is 1.07%. And this 1.0% is basically the ratio of all the bars combined together and make that area to be 1. Then what is that, or 100%? And then what is the ratio of the 9 and the 10 bars area? So if he doesn't know the difference between California and French wines, or if he doesn't know what he's talking about, then the right model is the one which says that the chance of being correct is 50%, right? If he's just bluffing, that he's going to say like randomly, right? And that is basically that we can apply this like a 0.5% model, okay? But this time, we don't know if he knows or doesn't know. So that's the question. That's what we want to know. Then let the blind tasting begin. That's actually finally like let's test it. Or another word, let's collect data. Then ask him to answer which California French wine. And it turned out 9 times out of 10 were correct. Okay. And then again, you remember, this can happen when you throw the coins and maybe like you get 9 heads out of 10. This can happen. But what is the chance of getting that? What is the chance of 9 or 10? In this case, 1.07%. Those like red colored area. Okay. So now, well, you can argue like, yeah, that can happen. So maybe, still, I don't believe he knows. Maybe it's just a random chance. You can argue that too. However, if we want to make decisions, which one is, suppose it would be more correct, right? So in that case, what's happening here is we collected the data, which is the right-hand side in the reality, the real world. Left-hand side, we assume that's random. Then it's actually not matching up. Those are not consistent. So that means the left-hand side model is not really explaining what's happening in reality, because 1% is happening. If you are told somebody that 1% chance it's going to rain and it rain, then you're going to blame that person or the weather forecast because it's completely wrong, right? 1%. But this is happening. So the model doesn't fit the reality. And at that point, we need to figure it out, or by inferring the truth about the world, by figuring out which model fits better with the data that in our hand. Okay, right hand side. So should we go with the P bracket correct, being correct, equal 50%, that model? We should go with that model. We should stick with that. Or there's another model, P bracket correct, being correct, is not 50% chance. Should we go with that model? So that's really a statistical inference. And then that's how we use a probability in a statistics or statistical inference. And of course, it can be like a 0.5 is like a precisely. What if like a 0.51, 0.49? What are we going to do? Right. So there is that variance that we need to consider. So it's not as clear cut as this, but this is a basic sort of like a framework of like having a probability as a sort of a model or the tool, if you will, to infer the truth or actually make decisions based on the data. Okay. So that's pretty much it for today, the probability. And I want to do this quick summary. So probability theory is a doctrine of a chance. It tells you how often different kinds of events will happen. And it is a branch of mathematics, not a branch of statistics. We use mathematics in statistics. Sorry, we use probability in statistics, but those are not in the same kind of doctrine as discipline. Okay, and the probability is about, you can use a P notation to express the probability, and then calculate the number of the events that you're interested in, and then out of possible all the number of all the events. Okay, but even if you know the theory, the probability is, this is why like it's part of the mathematics. All the mathematics is basically the theory. It is true, but it's a theory. But that doesn't mean that can happen in the real world, right? So that we don't know what is going to happen in the real world. However, because of law of large number, if you repeat over and over again, that even the reality start looking like what theory is presenting. So probability statistics, those two are deeply connected, but they're two different things. Probability is the model or the truth, but you don't know the data or you don't know the reality. That's a probability. Statistical inference is the opposite. You don't know the truth, you don't know the model, you have the data, but you want to infer that truth by figuring out which model fits better with the data. Okay, so that's it for today. Thank you for watching. Just a little thanks to at the end. So Our online seminar, so we're gonna, like I said, I haven't fixed the agenda yet, but most likely I'm gonna do the hypothesis testing next week, and then from there, a couple, hypothesis testing related topics, then eventually move into regression analysis. But online, when you go to our website and you go to the online seminar, you can see not only the future plans, but also the past seminars recording. So please check that out. And then also same menu under the run, you can see how-to tutorials and how-to video. So if you're exploratory users, please, you want to take advantage of those. And otherwise, if you have any questions, please feel free to reach out to me. My email address is kan@exploratory.io. And also we have the Twitter at Exploratory Data, where we announce everything about Exploratory. Okay, again, thank you so much for joining and watching. And with this, I'd like to open up the Q&A session.